Uh, Welcome back, everyone. We're going to explain Chapter 7, Section 1, which is chemical equilibrium. In systems that are in equilibrium, opposing processes occur at the same time and at the same rate. So bear in mind that when you talk about equilibrium, it doesn't say that two amounts of something can be equal. It only says that two opposing changes or processes are equal. For example, you might remember from chapter 1, when an excess of sugar is placed in water, at equilibrium, molecules of sugar are crystallizing at the same rate that molecules from the crystals are dissolving. So that was an example for physical equilibrium. Or we had another one, the rate of the evaporation of a liquid in a closed vessel can eventually be equaled by the rate of condensation of its vapor. So these two are examples of chemical or equilibrium systems, not chemical. Now, for a chemical reaction to be at equilibrium, the reaction must be reversible. So theoretically, every reaction can proceed in both directions, forward and reverse. So essentially, all chemical reactions are considered to be reversible, but they must be under suitable conditions. For example, under suitable temperature, concentration, or anything that can oppose or anything that can affect the equilibrium state. So reversible reactions can be indicated by this arrow, this double arrow, like this, like the one here. Generally, that's what we are going to use. But for irreversible reactions, which cannot be reversed, only a single arrow, one direction arrow is used. Let's continue for an example of a reversible reaction. For example, mercury 2 oxide decomposes when heated. So it becomes mercury, liquid mercury, and oxygen. But if mercury and oxygen in another container are also heated, of course, with a closed system is better, they will also produce mercury 2 oxide. So we can put mercury 2 oxide in one container, in a closed container, and uh, heat it until it reaches equilibrium. So if this is heating mercury 2 oxide, it will produce oxygen. After a while, this oxygen will form or will react with mercury again. It will produce mercury 2 oxide again. So the reaction will be like this. So in such a state, a dynamic equilibrium, both reactions continue, but there is no net change in the composition of the system. So there is no net change after it reaches equilibrium. It means that the reactant won't change and the product will not change as well. So if the whole thing can be collected under this uh, definition here, when the rate of its forward reaction in a chemical equilibrium, when the rate of its forward reaction equals the rate of its reverse reaction, and the concentration of its products and reactants remain unchanged. Look at this point. Concentrations of its product and reactants remain unchanged. It means that neither the concentration after it reaches equilibrium, neither the concentration of mercury, oxygen, or mercury oxide 2 oxide change, because it has reached equilibrium. Now, equilibrium can be a dynamic state, can have three types of or three states in equilibrium. In one of them, if more reactants react or more, the rate of forward reaction at first is higher than the rate of reverse reaction, and more product is formed, like here, more product is formed. So then the concentration of product here is a lot higher. Then it means that the reaction has gone towards the forward reaction and produced more SO3, sulfur trioxide, than the reactants. So we can say that products here predominate the reaction. But in another case, if more reactants are present than products, at that point, then we will say the reactants predominate and the reaction lies to the left. Equilibrium state lies to the left. But if concentration of both reactants and concentration of products are nearly the same, then the two arrows are also written in an equal way. But this is just for some certain types of reaction or some certain times which these arrows are used. We generally use for all types of reaction, we generally just use this symbol. Now, let's talk about equilibrium expression. Before producing an equilibrium expression, which must be at equilibrium, let's look at the rate of forward and reverse reaction in the beginning and at the end of the reaction. At first, the forward reaction, which we have the most reactant at first, the forward reaction starts at its maximum rate. So this side here indicates rate. This one's times 0 at the beginning of the reaction. And at the beginning of the reaction, we don't have any product. So the rate of product reacting to form reactants again is 0. It's not reacting because there is no product. But when the reactant starts and some reactants become products, some C and D are produced, so C and D also start to react. But since the concentration of A and B are gradually decreasing, because the reaction is getting forward, it's decreasing, and the rate is also decreasing. But at the same time, concentration of C and D are also increasing before it reaches equilibrium. So if their concentrations are also increasing, then their rates are also increasing until the rate of forward and reverse become equal. It becomes an equilibrium. What do you mean by dynamic equilibrium? It means that the equilibrium always moves, always. If some reactants, if a couple of molecules of reactants react to become products, at the same time the products will also go back to form the reactants because they are in an equilibrium state. So at that point, concentrations of reactants and products must remain constant. Now, how can we know by finding something, a value, if after equilibrium more products have been produced or more reactants are still remain? So we have to find, to answer that, we have to find K. What is K? K is equal to the concentration of products over concentration of reactants. So for example, for this reaction, A plus B becomes C and D. This is the, hold on a second, let me just, all right. This comes from this reaction. K is equal to C times D to the power of their coefficients, X and Y. All right. Now, K is independent of the initial concentration. What does that mean? It means that if you start with a high concentration of reactants or a low concentration of reactant, value of K will still be the same. Even if you change concentration after equilibrium and it reaches a new equilibrium, K will still remain constant. The only thing that can change K, which is equilibrium constant, is temperature. All right. So we talked about the value. Which values do we have for equilibrium constant? There are three values, A, B, and C. If we found out by the concentration of products and reactants that K is bigger than 1, then, as you can see from the expression, products on top, which is directly proportional with K, reactants in the bottom, which is inversely proportional with K. So if a higher value of K is present, it means that more products are present at equilibrium in that reaction. But if K is lower than 1, smaller than 1, smaller than 1 here means bigger than 0. For example, this is 0, it's bigger than 0, okay, and sorry about that, bigger than 0 and smaller than 1, for example 0.01, 0.02. K cannot be negative, it's not negative. When we say smaller than 1, it means that 0 to 1. But if K is equal to 1, it means that there is a significant amount of both reactants and products. We can see that products concentration can be equal to reactants concentration. All right. Only the concentration of substances such as aqueous and gases that can actually change are included in K. But pure solids and liquids, since their concentration can be thought of as constant, they cannot be expressed in K. K is constant for every reaction at a constant temperature. As long as the temperature doesn't change, then K is also constant. We use these brackets as mentioned in previous chapters for trying to express concentration. So this is the definition of equilibrium constant, and this is the definition of chemical equilibrium expression, which is each concentration is raised to a power equal to the coefficient of that substance in the chemical equation. The equation for K is also referred to as chemical equilibrium expression. Now, I have written a couple of examples here in order to write K. So if you want to put K or write concentration of the reactants and products in K, you have to look at gases and aqueous solutions. So for example, in this reaction, since both products and reactants, they all are gases, so we can write it like this: NH3 over, so since it's the product, but to the power of 2, sorry about that, so it's a power of 2 now, over nitrogen, concentration of nitrogen times concentration of hydrogen to the power of 3. But for the other ones, such as H2O, which is liquid, you don't have to write anything because it's liquid and it's not counted in our equilibrium expression. All right, let's write it down here. So for example, K for this one equals to concentration of H3O times concentration of OH, like this. All right. See, I have excluded the liquid here, so you can see it's over 1, like this. Sorry, it's not writing. So as you can just write, it's over 1, but you don't have to write the 1, of course. So the same thing applies here. You can write 1 over concentration of NH3 and HCl. Same thing here, CO2 over H2CO3. This is another example of equilibrium, which for hydrogen and iodine, where they react to become hydrogen iodide. So for this reaction, normally hydrogen is colorless while iodine is violet, and hydrogen iodide is also colorless. What does that tell us? So if this reaction continues, you can see the color violet normally fades away. If the reaction is irreversible, it has to fade away entirely and become a total colorless, but it actually doesn't. Even after a while, when it reaches equilibrium, a small a small amount of color violet will still remain in the container. That indicates the reaction it still contains some iodine. It means that the reaction is reversible and is at equilibrium. And also, for this reaction, we have a value of K, a general value of K here, which is like 54.34. This is an average. We mentioned before that even by changing concentration, K will not change. So look at this table also. Of course, as you can see, there are many different combinations of concentration of hydrogen iodine or hydrogen iodide, but still K is around 54. It's not changing, it's still constant. All right, there are a couple of notes if you encounter, and those are if the reaction changes and the K is given. For example, here A plus B becomes C and D, K is equal to 1. But if the reaction is reversed, you also have to reverse the K by putting 1 over the previous K. For example, if K is 4, it means that for the new reaction, K is 1 over 4. But if the reaction has been multiplied by a certain number, for example, now the reaction has been multiplied by n. If K is 4, then the reaction must be raised to a power of that number. I'm going to give you an example in a while.
For example, now if you look at here, for the second node that we talked about, if for this reaction, hydrogen and iodine becomes 2Hi, K is equal to 4. But if I multiply this reaction by 1 over 2, so the whole reaction becomes 1 over 2 hydrogen, 1 over 2 iodine, and 1 hydrogen iodide. So K was 4. Since I have multiplied the reaction by 1 over 2, then the K must be power to 1 over 2. Or power of 1 over 2 also means square root of 4. So square root of 4 equals to 2. Alright? Now, what if I reverse the reaction? It becomes 1 over, sorry, this one is equals to 54, my bad. So this is also 54. This becomes also 54. So the square root of 54 equals to 7.34. And if I reverse the reaction, for example, let's say the same reaction becomes Hi in a reversible reaction, 1 over 2 hydrogen and 1 over 2 iodine, then K3 is equal to, since we have taken from K2, K3 is equal to 1 over K2. So equals 1 over 7.34, which equals to 7.34 equals to 0.136. Alright, let's solve another question. For example, this question. This is practice 1, page 170 in your books. And the question says, at equilibrium, a mixture of nitrogen, hydrogen, and ammonia gas at 500 Celsius is determined to consist of 0.602 molar of nitrogen, 0.420 molar of hydrogen, and 0.113 molar of ammonia. What is the equilibrium constant for the reaction? So first you have to write K. K is equal to concentration of NH3. So this is the reaction. Square divided by concentration of nitrogen times concentration of hydrogen cube. So NH3 is 0.113, and that is square over concentration of nitrogen is 0.602 times concentration of hydrogen is 0.42 cube, and the whole result is 0.286, and that is the value of K. You can find the other questions also, like the. So I'm choosing from the section of question 9, which K is also given. Concentration of some reactions, the reactants are given. It asks for the concentration of the product. So here's the question: for reaction of hydrogen with iodine to become hydrogen iodide at 425. For example, concentration of both hydrogen and iodine are the same, which is equal to 4.79 times 10 to the power negative 4 molar. K is equal to 54.3. One concentration of HI is required. So how can you find this reaction or this concentration of product? First, you have to write the rule of K, which equals to concentration of HI in the reaction. HI is square, because as you can see it's the coefficient is 2, over concentration of hydrogen times concentration of iodine. We can say that HI square over 4.79 times 10 to the power negative 4 square, because they have the same concentration, equals to 54.3. If you want to find HI, so sorry about that, so equals to 54.3. So if you want to find the concentration of HI, HI would be square times 54.3 times 4.79 times 10 to the power negative 4 square. Take square root of both sides like this. Now you get the result, and the result is 3.50. 3 times 10 to the power of negative 3. Since its concentration, it's either molar or mole per liters.